Welcome to our episode. So let me take this opportunity to greet our school principal, Mr. Rex Laurazo, and to our department head, and at the same time, our assistant principal for junior high school, Ma'am Nida Ish Gumera, to my colleagues from the grade 7, 8, 9, and 10 teachers of the science department. Hello. Also to our viewers live from Facebook. Hello. Shout out kay Russell Chin, Rodelyn Mangiboa Sumili. Hi to Marjorie Balanay, Angeline Pañares Alagasti. Hello, everyone. And also to my family who are watching right now. So before we are going to proceed, let me share this quote to you. I took from Neil Armstrong. So it goes, mystery creates wonders, and wonder is a basis for man's desire to understand. One such wonder is understanding how Earth came to be and the continents also. So that is why for today's episode, we are going to focus on the possible causes and evidences that support plate movement. So I'm going to share to you on the screen, my presentation. All right. So here it is. Okay. Okay, so we're going to focus on the possible causes and evidences of plate movement. This is covered by quarter 1, week 2 for grade 10 science. Okay, so once again, I am teacher Annie Rose A. De La Cruz, teacher 2 of Iligan City National High School. Okay, so we are going to learn the objectives for today, which I took from the most essential learning competency for quarter 1, week 2 for grade 10 science. These are: describe the possible causes of plate movement, enumerate the lines of evidence that support plate movement. Actually, this lesson is quite a bit long, but we'll try to finish this one for this period. Okay, so before I'm going to proceed, I am posting here 3 questions. So how do we know that the Earth is ancient and changing? Do you believe that the Earth is really ancient and is changing? Okay, so don't you worry. I'm not going to let you answer this one first. We'll just proceed to these questions later. So we often think that because the Earth is a planet, it cannot change. And that is completely wrong because the only constant thing in this world is change. And we're going to relate to that. Okay, so the land that is on our planet is constantly moving and changing. Although these changes may not be seen, we know for sure that there are changes based on the evidences that have been gathered by certain scientists, okay, by various scientists that support this kind of plate movement. So another question being posted in there is that, how did the Earth's surface features form? All right. So what features am I referring to? So these features, surface features that I am referring to are the mountains, the volcanoes, and other geological features. All right. So let me ask you this question muna. Okay. So for the wonder guests and for our viewers also, have you been to any trips going to mountains? Or have you been into any mountains found in our country? I know for sure you already have been through, or you have been to these mountains already. Some of you have been to Mount Mighty Hilltop. Some of you have been to the mountains of Bukidnon, and for the rest of the mountains that you have been to in our country. So perhaps you would think that it might be different: all plains, no plateaus, and no mountains, right? Okay, so if it wasn't the same 100 years ago, how much more different is it? Okay, mga thousands and millions of years ago. All right. So for the third question, okay, so you have there, why are there volcanoes, mountain ranges, and earthquakes? So we're going to answer the question later as we go on with our discussion. Okay. So specifically, we are going to talk about the driving forces or mechanisms that are possible causes of plate movement. Okay, and also its evidences to support it. All right. So first of all, we have to know, it is important to know that the Earth's crust is divided or is being broken up by large pieces of tectonic plates. Okay, remember that these plates are pieces of the Earth's crust and upper mantle, okay, that fit together and move around the Earth's surface. And if you can see in that picture, you have there the different plates. You can see there the major and the minor plates. You have there the North American plate, Eurasian plate, and Antarctic plate. These are the major plates that you can see on the figure. Okay, so you also have there minor plates. Okay, I'm not gonna mention all of this na lang. So as you can see in there, you can also see arrows, okay? Arrows that are opposite in directions, that there are also arrows that move, slide past each other, and there are also others that meet together. Okay, so you have also there, as you can see in this figure, these are the lines, okay? These lines are what we call edges of the continents or edges of the plates, or shall we say plate boundaries. And you know what? In these boundaries, you can find the mountains and the volcanoes, and so do with the geologic processes, which we call earthquakes. So na-answeran na natin yung pangatlong question kanina na kung saan makikita, okay, ang ating mga, bakit meron mga volcanoes at saka mountains at saka earthquakes. Okay, so as we go on, mas ma-clarify pa natin yun. All right, so let's proceed. There is one question there I posted. What is causing the plates of the Earth to move? Now, this is a very challenging question. Geologists have been trying to answer. You know what? Kasi nga, wala pa namang nakapunta doon sa ilalim or beneath the Earth's surface, right? Because we have not been into there yet, all right? So, but then, kailangan natin answeran yan. What is causing the plates of the Earth to move? All right. So, let's proceed. All right. Plate movement. Do plates really move? Yes. Plates at our planet's surface move because of the intense heat in the Earth's core. Alam na natin yan na mainit talaga yung Earth's core that causes molten rock material or molten rock in the mantle layer to move. So I have here a video I took from YouTube, and I would like you to take a closer look at it and please observe what happens. All right, there it goes.
But the huge molten core contributes something else essential for life on Earth. A way of helping to regulate the planet's temperature. It's a remarkable system. Magma heated by the core rises towards the Earth's surface. As it spreads sideways, the Earth's crust is very slowly dragged apart. This moves the continents, creating the Earth's restless and ever-changing surface.
All right. So scientists really believe that there are really forces behind plate movement. And these are the possible forces that possibly cause plate movement. So scientists enumerated three. You have mantle convection current, you have ridge push, you also have their slab pull. So on the figure there, you can see the arrows that represent the direction of the plates. All right, so you have their ridge push, mantle convection current, and slab pull. We will explain that one later as we go on. All right. So I'm going to show you here another video on the possible causes of plate movement. So these are mantle convection current, ridge push, and slab pull. Take a closer look at this one and observe.
That this same phenomenon is what is happening inside the Earth. Liquid rock near the mantle is heated and rises toward the crust. The rock near the surface is cooler and sinks back down toward the core. This forms the same type of convection current which causes the plates to move. Scientists believe that this cycle of magma rising from the core to the crust and back again takes thousands of years to complete.
All right. So mantle convection current, as it was being mentioned, happens when the heat of the Earth's interior causes currents of hot rising magma and cooler sinking magma to flow, moving the plates toward the crust or along with them. So liquid rock near the mantle is being heated and rises toward the crust. So the rock near the surface is cooler and sink back down toward the core. So let's proceed. All right. So let us continue with another force, driving force that causes plate
At the top
movement.
of the mantle, the rock encounters the thin crust, and as it pushes it aside, lava flows out from the mantle to form new oceanic crust. As this happens, the plates smash into each other, slide past each other, or are pushed under another plate. This movement of the plate, along with the upwelling of the mantle by the convection currents, may also cause secondary actions that assist in plate movement. In ridge push, the mantle wells upward because of the convection and elevates the edges of spreading oceanic plates. Because these plates are higher at the spreading center, they are forced downhill due to gravity and eventually flatten out to the ocean floor. The great that this same phenomenon is what is happening, and it gives the plate a push along as new crust forms behind the plate at the spreading center. This is like those coin bulldozers at the fair where one new coin may push forward and knock others out of the way.
All right. So let's go back to the video once again. Kasi nga, na-proceed natin. So I'm going to explain to you what ridge push is. So in ridge push, the mantle wells upward because of the convection and it elevates the edges of the spreading oceanic plates because these plates are higher at the center, as you can see there in the figure. Okay, so they are forced downhill due to gravity and eventually flatten out to the ocean floor. The gravity here causes the movement down the ridge and it gives the plate to push along a new crust and forms behind the plate at the spreading center. All right, so let's continue.
It gives the plate a push along as new crust forms behind the plate at the spreading center. This is like those coin bulldozers at the fair where one new coin may push forward and knock others out of the way. Another mechanism that forms as a result of plate movement is slab pull. As the plate is pushed along, it may run into another plate. Oceanic crust is easily forced under another plate and back into the mantle. These converging boundaries can be identified by deep ocean trenches that mark the location where one plate is sliding under another one. As it slides under the other plate and is forced back into the mantle, gravity again works to pull it along, giving the plate another force to keep it moving. These two mechanisms are different. In slab pull, gravity is pulling on the front part of the plate. In ridge push, it is forcing that this same phenomenon, gravity again works to pull it along, giving the plate another force to keep it moving. These two mechanisms are different. In slab pull, gravity is pulling on the front part of the plate. In ridge push, it is forcing.
All right, so let us proceed. So slab pull occurs when older, cooler plates sink at the subduction zones. As you can see here, this one is the subduction zone. So cooler plates sink at subduction zones because they are cool. They become denser than the underlying mantle. So the cooler sinking plate pulls the rest of the warmer plate along behind it. All right, so let us have a quick review on the driving forces that cause plate movements. All right, so let's start with mantle convection current. Once again, this one happens when the heat from the Earth's interior, this one, causes currents of hot rising magma and cooler sinking magma to flow, moving the plates of the crust along with them. All right, so that's that one. Next, in ridge push, as you can see in there, the mantle wells upward, and this one is the highest portion of the plates. So plates are higher at the edges, and then gravity pulls downward towards this direction and flattens out to the ocean. So usually ridge push occurs at mid-ocean ridges as the result of the rigid lithosphere sliding down the hot, raised asthenosphere below the ocean ridges. And another one you have here, slab pull. This is part of the motion of the tectonic plate caused by its subduction. Subduction happens towards this part. So as you can see here, you have there, this one is plate 1, this one is plate 2. Plate 1 subducts beneath plate 2. So you have there slab pull. Just take a look at the direction of the motion of the plate. All right. So let us proceed. there's a question in there. Murag doubtful pag yun kaayo ang uban. Nga, tinuod ba yun? Totoo nga ba na nag-move ang mga plates? Okay, so do plates really move? Right. Wag na natin patagalin pa. Okay, so here are some of the evidences that support plate movement. So you have there very important key figures that are proponents of the evidences that support plate movement. All right, so you have there two theories. You have continental drift and seafloor spreading. So continental drift was proposed by Alfred Wegener. You pronounce it as Wegener. So Alfred Wegener, he was the one who proposed a theory on continental drift. And another key figure here, this one is Harry Hess, together with his team, Robert Dietz. Okay, so together they work as a team so that they'll be able to come up with a theory on seafloor spreading. So we'll just explain this one later. All right, so let's start with the first evidence that support plate movement. All right, so what is continental drift by Alfred Wegener? According to him, or according to his theory, the continents were once a large landmass. All right, this landmass is what we call Pangaea or Pangaea. Okay, Pangaea. So Pangaea is a Greek word which means all earth. So this Pangaea started to break into two smaller supercontinents. He called it Laurasia and Gondwanaland. I was not able to label this one as Laurasia and this was Gondwanaland. Laurasia is on the upper northern hemisphere and the other one, Gondwanaland, is on the southern part. All right, so these smaller supercontinents broke, separated, and drifted apart since then until the present day continents that we have right now. So here I'm going to show you another video that continents really drifted apart according to Alfred Wegener of the continental drift theory. All right.
Continental drift. Let's travel back in time and watch continents move. Moving back in time, the Himalayas and Mount Everest disappear as the collision between India and Asia is reversed. Climates are changing. Australia joins Antarctica as India approaches. Going back 150 million years, the continents are joined in three large pieces. South America and Africa are on one landmass. India, Australia, and Antarctica form a second. North America, Europe, and Asia make a third. 225 million years ago, the supercontinent Pangaea exists. Let's watch this movement as it occurred going forward in time. As Pangaea splits into three large pieces, the Atlantic Ocean starts to form. India starts its race to collide with Asia. As the continents take their current locations, India and Asia collide, and the Himalayas and Mount Everest appear. What is next?
All right, so that's
Continental-
it. So, how do we prove that this supercontinent Pangaea separated and drifted apart? Paano yun na-prove ni Alfred Wegener ang kanyang theory na talagang nagdidrift ang mga continents? So, this time we are going to explore as to what evidences Alfred Wegener has presented. So, syempre, may mga ebidensya yan. Alright, so that masupport niya yung theory on continental drift. So, these are his evidences that he presented to the scientific community so that he can prove that really the continents have drifted. So number one, we have their evidence from fossils. And you also have there, number two, the continental jigsaw puzzle fit of the continents. Third one, you have their evidence from rocks. And fourth, you have paleoclimatic evidence. All right, so let's proceed. Okay, so evidence from fossils. you know for sure what fossils are, di ba? So these are the remains of animals and plants millions of years ago. So when identical species of plants and animals are found in the different locations of the continents, it really proved a strong evidence that everything was once a single large landmass. As you can see in there in the picture, you have their extinct plant Glossopteris, which is found or which were found in South America, Africa, India, Antarctica, and Australia that are now separated. All right. So that these continents in which the Glossopteris fossils were found were already far from each other as to the present locations. So the large seeds of this Glossopteris plant, extinct plant Glossopteris, are very the seeds of this extinct plant are very large. So kung iisipin natin, right? Kung iisipin natin, napakalaki ng mga seeds na ito for them to travel, or it is not possible for the seeds of this plant to travel a long journey by wind or could survive a raft ride through the ocean. So napaka-imposible nun. So what does this one imply? So masasabi talaga natin na the continents before were once connected. Right? So let's proceed. Another evidence from the fossil of freshwater reptiles, which are found in South America and Africa. So the fossils that were found were Mesosaurus, Lystrosaurus, and Cinognathus. Okay, so Mesosaurus and Lystrosaurus are freshwater reptiles found in South America and Africa. You also have there Cinognathus, a mammal-like reptile found in Africa and Argentina. All right. So fossils of these animals were discovered in different continents being mentioned. So these are freshwater reptiles. So napaka-imposible naman na itong mga reptiles na to, napaka-imposible na that they were able to swim over vast oceans and move from one continent to another. So ano talaga ang ibig sabihin nito? What does it imply? So it implies that these continents were once joined and connected. Okay, let's proceed. So Wegener used fossil evidence to support his continental drift hypothesis. So the fossils of these organisms are found on lands that are now far apart. So combining all the paleontological evidence discussed, these fossils can connect the continents based on their distribution patterns. Okay, so they are distributed to the different parts of the continents presented here. So this gives us the second evidence of the plate movements, which is the apparent fit of the continents. So the coastlines of the continents, as you can see in here, even if we're not going to take into consideration the distribution patterns of these fossils, you can see that it will still fit together like puzzle pieces. So as you can see in here, much like a jigsaw puzzle fit. Okay? So in the next picture, I'm going to show you here South American continent and Africa. All right. Similarly, kung titignan natin yung mga shoreline ng South America at saka Africa, if they are being placed together, they are a good match for fitting. No? You can fit them together. Okay? So this one shows the continental puzzle fit of the two continents. All right. So continents look like they could be a part of a giant jigsaw puzzle. So look at this one. Look at the figures. So that's it. These continents almost fit together perfectly. All right. So the continents fit together like this one. Okay. So this is how they looked 250 million years ago. All right. So another evidence that Alfred Wegener presented were the evidence taken from rocks. As you can see in there, in the picture, you have their rock and mountain correlation. As you can see in there, in the first continent there, you have their mountains. And this one, another mountains. So these mountains share similar characteristics. even if they are separated by this vast ocean in here. So what does this one imply? All right. So this one implies that the continents were really next to each other, or they are once connected to each other. And in the figures here at the bottom, you can see the Appalachian Mountain Range, which are found in North America, which is also which has also similar characteristics as to the mountain range found in eastern Greenland mountain. It is eastern Greenland. All right. So they share the same characteristics. So here, Wegener's map also helps to explain the similar matching rock formations that are found oceans apart. This one. These continents share the same rock correlation. All right, rock or mountain chain correlation. How do the scientists know that these rocks are or have correlation? So they used a method called radiometric dating. So this technique is used to date materials such as rocks and carbon. So scientists have found out that these rocks on this continent, found in these continents, have really matching correlation. All right. So as you can see here in the figure, also you have their Appalachian Mountains in the North America, which share the same characteristics on the mountains of Africa. You also have there the characteristics of the mountain ranges found in Greenland and Norway. They share the same characteristics, just like also the mountain chains that were found in South America and Africa. Okay, so what does this one imply? So this implies that the continents were once connected to each other. Right. So the next evidence I'm going to show you is the glacial evidence that were found on the continents of some of the tropical countries and some of the polar continent, like Antarctica, South Pole, India. So in this, probably this glacial striations or glacial marks, when these continents have drifted, it left marks over here. These marks are what we call glacial striations or glacial scars or glacial scarring. All right. So that is also one of the evidences that was supported by Alfred Wegener in his continental drift theory. All right. The next evidence that I'm going to show you is about the paleoclimatic evidence. Okay. So as you can see there in the picture, you have their European coal mines match up with coal mines in North Africa. Okay, so you have there, you can see the coal beds that were found on the different continents. There were coal beds that were found in South America, North America, Europe, Asia, and even in Antarctica. Now, itong coal beds or coal deposits ay na-form through the compaction and decomposition of swamp plants. All right, that lived millions of years ago. So these coal deposits ay na-discover in this continents. Even in South America, Africa, Indian subcontinent, Southeast Asia, and even in Antarctica. So maitatanong natin, how come merong coal deposits na na-form sa Antarctica when it's a very cold region? Okay? Meron bang nakakapag-survive na plants doon when in fact it's a very cold region? So maiisip talaga natin na hindi iyon ang original position ng Antarctica ngayon. Antarctica noon. Okay? So posible na ang landmass mismo ay nakapag-experience ng tropical na klima, malapit siya sa equator. So that we can come up in our mind na talagang bakit may cold beds sa Antarctica? Siguro ang Antarctica ay not located in the present position right now, but it's located near the equator. Kasi nga may cold beds. Cold beds are the result of the action and decomposition of plants, swamp plants. Okay? Probably that's the original position of the Antarctica. Malapit talaga siya sa equator. All right. So definitely, that holds strong evidence that continents were once connected before. All right. So in the figure here, you can also find the different coal swamps, coal deposits are found in different continents. So with all these evidences used to support the continental drift theory, unfortunately, all right, the scientific community did not accept Alfred Wegener's continental drift theory. Bakit? Alam niyo ba? All right. So hindi siya natanggap kasi nga hindi na-explain ni Alfred Wegener kung ano talaga yung dahilan kung bakit siya nagdi-drift. Nahirapan talaga siya sa pag-explain. So hindi niya ma-explain yung talagang driving force which is enough to move these continents, which is enough to move the continent apart. So doon, hindi siya na-accept yung theory sa scientific community. Alright. So, because of that, there was another set or another team who proposed another theory that was later accepted by the scientific community. And this one is the theory being presented by Harry Hess and Robert Giles. So according to him, hot, less dense material from below the Earth's crust rises towards the surface at the mid-ocean ridge, just like in the figure being shown on the left. All right, so this material flows, carrying the seafloor away from the ridge, which creates a crack in the crust. So the magma goes out of the crack, goes down, and becomes the new seafloor. So, sino ba itong si Harry Hess? Siya nga pala ay isang geologist from Princeton University in USA. And at the same time, he is a naval commander during the World War II. Okay? So one of his missions is to find submarines that are located in the deepest parts of the ocean. But what he found out was very intriguing to him. He found out a ridge, okay, a mid-ocean ridge. Okay, bakit nga niya na-found out ito? Because they were using sonar. Sonars are used in finding submarines beneath the oceans. All right, through the sonar, he was able to get a picture of a mid-Atlantic ridge shown in the figure here. So here's a map of the mid-Atlantic ridge he found out, okay, using sonar. Right, all right. So yung mid-Atlantic ridge na yan ang simula ng pag-iisip kung meron ba talaga siyang connection doon meron ba talaga siyang answer doon sa theory ni Alfred Wegener na hindi na-accept ng scientific community. So here, in the picture, you have their mid-Atlantic ridge formed due to the separated tectonic plates on both sides of the ocean. All right. So, I'm going to show you here how seafloor spreading happens. Right. So, this one. All right. So that's how seafloor spreading happens. As you can see here in the figure, you have the blue stripe here and have there another stripe. I think this one is brown stripe. All right. So as the new crust is being formed at the center, it is being pushed sidewards. All right. So you have also there the north and south magnetic pole. Okay. So this one. Seafloor spreading was strengthened when there was a discovery of the magnetic rocks near the ridge, and we call it magnetized stripes. So these stripes hold a record of the reversals of the Earth. Okay, I'm gonna play this one again. So every time na mag-produce siya ng new at saka the old crust are moving sidewards, there was also something that is happening over the north and magnetic poles of the Earth, right? We call it magnetic reversal. That one again. So ito talaga yung hindi na-explain ni Alfred Wegener bakit nag ang mga continents. Alright. So, much like Alfred Wegener, Harry Hess has to provide evidences for seafloor spreading in order for his theory to be accepted by the scientific community. So here are his evidences. All right. Based on the theory, right, based on the evidences of Harry Hess on his seafloor spreading theory, found out that rocks are younger at the mid-ocean ridge. Rocks, okay, that are far from the mid-ocean ridge are also older. So here, ito yung ridge, okay, mid-Atlantic ridge, mid-ocean ridge, ito yung ridge. Right. Mas younger ang mga rocks na nakikita dito sa bandang dito. At saka, yung mas malayo sa ridge, these rocks here are older. And they also found out that sediments are thinner at the ridge. Mas manipis yung sediments na nakikita dito sa bandang mid-ocean ridge. At saka, mas thicker dito na mas malayong parte ng mid-ocean ridge. So, the fifth evidence that he presented was that rocks that make up the ocean floor near the ridge follow a pattern of magnetized stripes. I have shown that one already. Right. So what is magnetic reversal? This is also one of the evidences that plates really. What is magnetic reversal?
Is made up of different layers. And one of those layers, the outer core, shown here in orange, is composed of molten metals, including iron and nickel. Now, those molten liquid metals are not sitting still, but rather they are flowing around the inner core. And the movement of that liquid metal generates a magnetic field, which essentially turns the Earth into one gigantic magnet. Now, the fact that the Earth is a magnet and has a magnetic field is very important for a lot of different reasons, which we won't get into in this video, but it's important that you know the Earth essentially is a magnet. And just like a magnet that you would play with, it has both a north and a south pole that behave a little bit differently and are detectable. Now, a strange phenomenon we have seen on Earth is that the magnetic north and south poles switch periodically over time. So if you look at this visualization, let's say that the orange area represents the magnetic north and the blue represents the magnetic south. Now, over time, those poles will become kind of all haywire and then eventually flip so that north has become south and south has become north. This is known as a magnetic reversal, and we see it happen on a fairly regular time scale throughout Earth's geologic history. Now, here's why this is so important and relevant to seafloor spreading. It's because these magnetic reversals are.
All right, so that's it. That's magnetic reversal or the magnetic flip. Hindi ibig sabihin na yung North Pole, mababaliktad yung Earth. Yung North Pole magiging ano siya, South Pole doon sa baba. Hindi. Only the magnetic flip. Okay, so there are some points in history that the North Pole flips and becomes the South Pole. Right. So that's it. So that is magnetic reversal, which is found or which was being presented by Harry Hess. So may mga ebidensya yan at the bottom of the ocean. So these magnetic stripes are found at the bottom of the oceans. Specifically doon sa mid-oceanic ridge. Right? So I hope marami kayong nalalaman for